All right, guys. So section 9.4. Let's finish her up. This is going to be the last of the required content for the semester. Again, I apologize for not having this out sooner. I maybe you saw in the announcement I had finished it, but for my microphone was dead when I did the video the last time, and so now I'm having to do this thing over from scratch. So let's just go ahead and get through it, right? So we want to talk about backwards chaining in first order logic, and we want to look at a high level an algorithm for getting her done. Okay, so algorithms that use backwards chaining, they are starting with a goal, and you're trying to find a fact that supports your proof. So, you're going to start off with the fact that you want to, you start off by assuming that West is a criminal, and then you work backwards through a series of implications to arrive at some starting set of facts. And if you can do that, then your proof has been proven, right? Then you've gone through and said, oh yeah, I've proven that Colonel West, I think that was his name from the last video, was a criminal. Now there are some disadvantages to a backwards chaining algorithm where you start off with your proof by starting with the goal, and we'll get into those a little bit later. But there are some things that are disadvantages. So the backwards chaining algorithms, these are used in logic programming. Matter of fact, this is what Prolog does. Prolog uses in its inference engine backwards chaining, okay, to answer queries. And so this is the most common form of automated reasoning, right? Of reasoning that's done by computation, right? So let's take a look. So the backward chaining algorithm introduced by the text, which we will talk about briefly, which we'll give an overview of here. It's called FOL BC ask. So, first order logic backwards chaining ask algorithm, and you can prove your proof if the knowledge base contains a clause that has this form, right? So you've got an implication where you've got your left-hand side, and that's a bunch of conjuncts, A and B and C and D and E, right? And on the right-hand side, that's your goal. That's what you're starting with. So, F, right? So left-hand side, form, this is the form, bunch of conjuncts, and the right-hand side is that thing that you're trying to prove. So in the example we're going to look at, I'm going to bust out the whiteboard and walk you through it. We're going to go back with what we had in the previous video where we're trying to prove that, West is a criminal. So that's our goal clause, right? That's what we're trying to prove. Now, if we can satisfy a bunch of the conjuncts on the left-hand side, A and B and C and D, right, then that would mean that all of those are true, and then that would imply our goal clause, which is that West is a criminal, okay? Now, a couple of notes here, a couple of things to note, right? We have a sentence like this, American West, right? That's an atomic fact, okay? And that's considered a clause with an empty left-hand side. And that's going to be useful for us a little later on as we go through this. Now, if you've got a query that contains a variable, right? So, the goal is person X, for example. Now, you could prove that query, you could do that proof. It can be satisfied in multiple ways, right? You can have a whole list of substitutions that might work out. So, substituting John for X, right, for the goal part here, that might get the job done. Satisfying Richard for X for your goal, that might get the job done. And so because of that, the algorithm is known as a generator algorithm. So basically it's a function that returns multiple times, right? And each thing that's returned is one of the possible results that you could have. Now you look at it, you're like, well, how can a function return multiple times? Well, it can't, right? I mean, once you return from a function, the function's over. But if you return a list that contains possible results or possible solutions, possible substitutions, then that works, right? So think about C++, returning a vector, Java, returning an array list where, each element is one of the possible substitutions, one of the bindings between the value and the variable. Think about Python where it's just a list. Think about Lisp, you're returning a list. So when you think about it that way, well, okay, okay, fine. Hey, you can return multiple times, right? Now, the backward chaining algorithm, it's going to be a type of and or search, right? So this is going to be similar. You'll notice some similarities between this and the and or search that we looked at back, in earlier chapters, for stochastic searching. So there are a couple of required parts. There's the or part and there's the and part. Okay, now the or part, what is that? Right? That is the part where you have different rules in your knowledge base might all have the same right-hand side, right? So imagine if you had, 4 sentences that look like this, right? And each one of them, the goal, the right-hand side was criminal west, right? So there'd be 4 choices. If you could solve any of those sentences, right? If you could satisfy all the conjuncts on the left-hand side for any of them, well, then you prove that west is a criminal, right? So that's the or part. Okay, a goal query can be proved by any knowledge-based rule. Now the and part, all the left-hand side conjuncts must be proved, right? So you have a goal query, right, that has a rule where the goal is on the right-hand side. And so on the left-hand side, you've got the 4 conjuncts. Now all 4 of those have to be dealt with. A and B and C and D, right? So A has to be satisfied and B has to be satisfied and C has to be satisfied and D has to be satisfied in order for the implication itself to be satisfied, right? In order for you to prove the goal part of the implication, right? So that's the and part. The or part, hey, any rule that you have with that goal query, with that goal clause on the right-hand side, either one of those could be used to prove your goal, right? But once you have one, the and part is every single conjunct on that left-hand side has to be proved. All right, so at a high level, how does the or part work, right? Well, it does, and I'll point this out when we look at the algorithm. I'll point out the pieces and then let you trace through and encourage you to interact with the material by letting you chase through the algorithm on your own to get a good feel for it. But what does it do? It finds all the clauses that can unify the goal, right? Then it needs to standardize those clause variables so that they're brand new, so you don't have any repeats, okay, within your knowledge base, right? So if the right-hand side of that rule does unify with the goal, right, then the or part has to go through and prove every left-hand side conjunct using the and part, right? So in other words, let's go back up here. If you can unify for the goal, then or turns around and uses the and part of the algorithm to prove every single one of the conjuncts on the left-hand side. That's what that's saying. Okay. All right. So how does the and part work for the algorithm? Each one of the conjuncts gets proved in turn, right, until it can't. I mean, if you can't prove any of the conjuncts, then it fails, right? And then the or part can move on to another clause that might unify with the goal, right? But the and part tries to prove each of the conjuncts, and let's just say it keeps track of the accumulated situation, right? It keeps track of how the proof is progressing, how the chaining's progressing. All right, so here's a proof tree for criminal west. We're trying to prove that criminal west, or that west is a criminal. And so this is a proof tree that's backwards, you could say. It kind of mirrors the forward chaining algorithm that we looked at before. So what I want to do now is I'm going to switch over to the whiteboard, refresh your memory on the knowledge base that we put together for talking about you're a criminal if you sell weapons to America's enemies. And then we'll build this proof tree, step by step. So let's review that knowledge base we put together in the previous video, and then we'll apply, we'll have a run through of the backwards chaining algorithm that the textbook presents, and we'll demonstrate how that works. It's a form of depth first search, basically. But anyway, so let's go through the knowledge base again. Rather than writing out A for American, W for weapon, S for cells, H for hostile, C for criminal, and so on, I just abbreviated, I just used the first letter of each of those words. Okay, so what was that first sentence? That first sentence, remember all these things, with the exception of this fact and this fact, all of the rules are, in fact, are universally quantified, right? So rather than having to, specify for all X, Y, and Z, for this first rule, it's just a given, okay? All right, so let me erase that. All right, so what was the first sentence? If you have an American, right, some American, who's we refer to as X here, that's the variable, and there's a weapon Y, and there's a hostile nation Z, if that American X sells weapon Y to hostile nation Z, if all of these things are true, then that's going to make that American X a criminal, right? So that's what that first rule said. Now, we had a couple of sentences here that were the results of existential instantiation. So this fact here owns. We said there exists this thing that we call M sub 1, and no owns that thing M sub 1. And then with the next fact, we said, well, that thing M sub 1, it's a missile. Okay. Now the next sentence, remember what this was saying, is that if there is an X that's a missile and no owns that X, then that implies that West sold that X to no, okay, the country no. And then we had to specify with a rule that a missile is a weapon. So for anything that's X, if it's a missile, then it's a weapon. And then here we had to specify with this next rule, we had to satisfy, well, anything that, any X that is an enemy of America, if that's true for some X, then that implies that that X is hostile, right? And then we knew that West was an American, and we also knew that no was an enemy of America, okay? All right, so let's trace through this algorithm, right? So you start off not with some top level facts. Instead, you start off with the goal, that thing that you're trying to prove, right? And so the thing that we're trying to prove was that West was a criminal of West, okay? So remember, that's going to be the right-hand side of that first sentence, that first rule in the knowledge base. So in order for us to conclude that West is a criminal, to be able to prove it, we have to resolve each of the conjuncts in the left-hand side, right? And this is done in a depth-first search kind of way. So we have to satisfy A of X, right? So, there's going to be 4 total conjuncts that have to be satisfied, right? So I'll put the ands that separate them in between, all right? So the first things first. So A of X, right? So is there anything in the knowledge base that can unify with that we can substitute for A of X that matches? Well, yeah, A of West, right? So we can go here and say, all right, that West, if we put it in for X here, because here for this right hand side, right, we have a binding of X of West, right? So if we fill in West for A of X here, do we have anything that matches? Yeah, we got the A of West, that fact right there. So we can go ahead and say A of West. So that first conjunct, that guy's satisfied, okay? Now the next one we have to deal with is the weapon part, right? So W of Y. So we need to find some binding to y that will satisfy it, right? So if we look at w of y, okay, what have we got? Is there anything in our knowledge base that we can use, right? Well, there's no standalone fact, but there's another implication, right? So we can use this implication right here, okay? So what happens then is that this term right here, that becomes a new sub-goal, right? So that means then that we're going to recursively have to then deal with this left-hand side, okay? Now that left-hand side is m of x. Is there anything we can bind to that, right, to help us out, to satisfy that? Well, if we look at this fact right here, right, we can bind to that, right? We can bind to that m of 1, right? So we can say m sub 1, okay? And so then that m sub 1 goes in here. Oops. And then it says, well, that's a missile, right? That's a substitution we can do, right? Now this propagates back, it backs back up, and so that m1 will also go right there, right? Because we went through and we said, oh, well, because if you look at this sentence here, m of x implies wx, right? So if we substitute in here m of 1, then we get w m of 1, right? So it backtracks through. That substitution goes all the way through. It satisfies both sides, and so now we can conclude that this is weapon of m1. Okay, this was a subgoal, and it's been satisfied. So now both of these conjuncts are done, right? So that's done, and that's done. So now we back up, and the depth first search continues. Now it's time to deal with this third conjunct, which is cells X, Y, Z, right? So let's look in the knowledge base and see if there is anything that matches, right? Well, this is the only other term where we've got our only other clause where we have, cells, right? So we're going to go ahead and use that one, and we're going to have to recursively prove the left-hand side again. So we plug this in, right? So west, and then we've got we're going to have, let's see here, plug in west x, no, okay, west x, no. So what we have to do is we have to find a substitution for that x right there, okay? And we're going to have to go about doing that by looking at the left-hand side, right? So the depth first search continues, right? So we have to prove both sides, or both conjuncts in this left-hand side. Now, for m of x, right, was there a fact in our database that we could unify with? Yep. So we can bind m1 with x, right? And then that'll satisfy this guy. So m1 goes in here, right? And then we back up and the depth first search continues. Now what was the right hand side? O of no x, right? Now is there anything that unifies with O of no x? Is there any term in here? Well, let's go see right here. Here's a fact. O no m1. So there's a binding for x for that term. Right? There's the binding. So that becomes m sub 1. And so we've now satisfied that term. So since we've satisfied both those terms, right, we have a binding for x, then that right hand side, that subgoal, has then been resolved, right? And so what was the binding for x? M1. Okay, so now that third conjunct has been dealt with. Now what about the last one? H of Z. Okay, so the depth first search backed up all the way to the root, and now it's proceeding to deal with the last conjunct, right? So how can we resolve H of Z? Is there any fact in here that is, this is not an implication, just its own atomic clause? Is there anything here that matches with H for hostile? Nope, but we do have another implication. So we recursively, do the same deal here, right? So we got the right hand side, that's this. So we have to deal with the implication part. Okay, so E of, let me move this over, E of X America, right? Okay. So, I mean, these right here, I mean, you're looking at them and you're going, well, they don't match, they're not the same, Z and X, right? These are just, generic names that we can have for standing in, right? In the knowledge base, we read them as X, but that term, that term here, that's defined, that variable is defined within the clause itself, right? That's just referring to a placeholder, something that can change, right? And so it's useful for defining the meaning of the sentence itself, but remember, this could be anything. That Z could be anything. This X could be anything, right? So the fact that they're different variable names in the different terms within our tree here, and that they're different names for different variables in the different clauses within the knowledge base, it doesn't matter, right? That's only there's you can think of them as being in scope for their own sentence, right? This is just saying there's some Z which is different than the X and the Y, but that's still something that you can put in. So for what we're doing here, essentially the X is going to equal the Z, right? These are just names for unknowns. That's all it is, within different contexts, within different scopes. Okay. All right. So I mean, we can look at this and say, well, there's some item X which we can use to satisfy Z over here. You can think of it that way. All right. So let's go back. Oops. Maybe I can zoom out a little bit to make this all. Nope, there we go, a little bit better. Okay, cool. So let's take a look at this left-hand side, E X America, which implies H of X, right? So this is another subrule. So let's see if there's any fact in the knowledge base, and there is, E no America. So what can bind with X here to satisfy, to unify that term? Well, the no, right? So X, no. So that no replaces the X. That's the substitution. So let's put it in there. Right? So this clause, this term, this has been satisfied now. So the left-hand side for this implication is satisfied. So then the right-hand side is going to be true, and it's going to be dealt with. So we can substitute in the no. Okay, and so then that satisfies that fourth conjunct. Okay, so American West, M1's a weapon. West sells weapon M1 to no, and no is hostile. So all four conjuncts have been proven through this backwards chaining algorithm. And since the left-hand side, all the conjuncts have been proven, that means that this guy right here has been proven. So we can conclude, or we can infer, or we can deduce that West is in fact the criminal. Okay, so that's how it works. You start off with whatever the thing is that you want to prove, and that's going to be the right-hand side of some rule in your knowledge base, and the or part would come in if I had several different rules, right, that all pointed to criminal X. Because if any one of them, we could prove all of their conjuncts on the left-hand side of the rule, then any one of them would be able to be used to prove that West is a criminal. So that's the or part. The and part comes into play when you have to prove every single conjunct in that left-hand side. And it's just recursively applied, because we might have had, as we just saw, might have had another rule in the knowledge base, D implies G. Well, the prove, or sorry, I did that backwards. G implies D, right? So to prove the D, we'd have to then recursively go through and do it again, and prove G over here, so that way we can satisfy D over here, which then would prove the D conjunct, right? So it's just recursively applied. All right, so we're back to that proof tree, and you can see, that it has the similar shape to what I just did, right? So to prove that West was a criminal, we had to prove American West and weapon Y and cells West M1Z, right? And hostile no-no. But weapon Y, we had to recursively prove its left-hand side, which was missile Y. For cells West M1Z, we had to recursively prove its left-hand side, which was the conjunct of missile and owns. And then for hostile no-no, we had to recursively deal with its left-hand side, right, which was enemy no-no America. Right. So as I was pointing out, backwards chaining is a depth-first search, and because of that, it has linear space requirements. But since it is a form of depth-first search, it does have problems with repeated states and completeness. Well, what does that mean? Remember when we looked at depth-first search back in chapter 3, and we had a problem where you might be able to regenerate the same state in the same subtree. Well, repeated states, right? Something similar to that could happen here as well. So here's the complete algorithm from the textbook, and I'll just point out a couple of things. I really mean it this time. And I'm going to resist all temptation to go through it line by line with you, in the interest of time, because we don't need to, right? You're not going to be asked to write code for this on the test or anything like that, or to implement it, because the beauty of it is that Prolog, which is what you're doing your last project in, a backwards chaining algorithm is implemented in its interpreter, in its inference engine. It does all the heavy lifting for you. It does this for you on the back end. Okay. But anyway, so we got three functions here. It uses indirect recursion. You got the driver function, which starts everything. You give it the knowledge base and the query, and it returns a generator of substitutions. So remember when we were talking about generator, there could be multiple answers to solve a query, and so you could see that, right? So remember we talked about how you could return that as a list, or as a vector, or as an array list, or what have you. So this is just saying, look, this could return multiple substitutions that could satisfy the problem. And when you're working with your expert system for Prolog, or getting used to Prolog, sometimes the answers that the inference engine gives you is like, say, X/John, X/Richard, X/Tim, X/Kate, right? Those are all substitutions that could work to satisfy your query. So you'll see that tie in as you go through and work on it, right? So it starts off by calling the OR, and you can see there's the OR and the AND parts we talked about, similar to the AND/OR algorithm from the previous chapters. So it's saying for each rule, left-hand side implying right-hand side. So fetch rules for goal. This just means, get all of the possible rules that have the goal as a right-hand side, right? And then standardize the variables as we were talking about, so you don't have repeating variables. I mean, that goes to the standardized variables part. A second ago when I was talking about, hey, this is X and this is Y, and they're independent of each other in their own scopes, and blah, 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 blah. That's what standardized variables is pretty much taking care of for you, right? And so then you can see that you have a call to AND. It's attempting to do unification. And then the AND part is going through and evaluating each of the conjuncts, right? It's going through and working on each of the conjuncts. So, trying to prove that each one is done by doing a substitution, like we were doing when I was walking you through the algorithm. Okay, so again, you don't have to memorize this pseudocode, and I'm encouraging you to trace through it on your own to see, how it works out, to get a feel for it in general. But you're not going to have to implement it. You're not going to have to write, code for this. And what you want to be able to do is what I did on the whiteboard. Okay, and that's what this algorithm does, is what I was doing on the whiteboard. So, try it on your own. Grab a piece of paper, have the algorithm up in front of you, and see if you can trace through what I did on the whiteboard and see where the pieces fit in. Leaving that to you on purpose to try to force you to interact with it. Okay? And if you're having a hard time seeing it, don't forget, got a link on Blackboard to source code repository for implementations of all of these algorithms, right? So I would say, try to do on a piece of paper what I did on the whiteboard, follow, see if you can tie that in to the pseudocode. But if not, you can use the source code, right? So go take a look at the source code in the repository. Use that kind of as a cheat sheet. You're like, I'm not exactly sure what this means. And go look at the Python implementation, right? Python's easy to read, even if you've never programmed in Python before. I mean, the syntax for the language is really, it's pretty obvious. It's an easy to use language. All right, anyway, so let's talk about logic programming. The most widely used programming language, Prolog. And so that's why you're getting some exposure to it. Okay. A lot of expert systems are written using Prolog, so guess what you get to do? You get to write an expert system using Prolog. But it has applications other places too. For example, compilers, a lot of compilers use Prolog to accomplish its goals for its tasks. It's also used to help parse natural language, like human language. All right, so here's some notes on Prolog, and hopefully you've already noticed this, right? Hopefully, if you've already gone through the tutorials, if you already watched the sample videos I did on this, then this is just going to be like, oh yeah, okay, cool. Now I can kind of see it tying in. Or maybe after you watched the videos, saw the tutorial, read through the tutorials, you were like, I am still a little fuzzy. Well, maybe this will be an opportunity for me, or for the text, to tie them together, first order logic and Prolog. Your Prolog program, right, what that is it is a set of definite clauses. That should say definite clauses, not definitive. Okay, so the knowledge base that we had for the kernel West is a criminal problem, right? That was a set of definite clauses. We had two types of clauses in that knowledge base. We had the implications, which we referred to as rules, and then we had, atomic clauses, which we referred to as facts. Rules and facts. Rules and facts. And so you'll see that language over and over and over again when you're reading up on Prolog, because that's what the programs are built around. Rules and facts. And those rules and facts then can be used to perform queries, to ask questions of the expert system, and by using a backwards chaining algorithm, which is what Prolog uses, you can get answers to your queries. What should I do now? Is there a train that goes from San Jose to Monteverde? Can I take a plane flight from California to Texas to Maine? Okay. All right, so definite clauses, a little bit different syntax than the first order logic, but that's what you're capturing. You're capturing clauses from first order logic. That's what the statements in Prolog are. So uppercase letters are used for the variables, lowercase letters are used for the constants, so that's the opposite of what first order logic was doing. Now, for the conjuncts in the clauses, first order logic, you use those upside down V's, right? In Prolog, they're commas, okay? And the implication clauses, they're written backwards. They're written backwards, okay? So take a look at this right here. A and B implies C, right? So that's your first order logic. Now, if we were to write that in Prolog, you'd write it like this, right? There'd be a period at the end after the B too, which I left out because there's no period in the first order logic clause. But anyway, you'll see some examples out here in a second. So this right here is Prolog syntax. And so you can see that to the right of this little weird thing, this is the arrow, okay? The arrow replacement, it's a colon and a dash. But on the right-hand side are your conjuncts, right? Which are the left-hand side in first order logic. So this is saying A and B. So A and B have to be satisfied or have to be proved in order for C, right? In order for us to conclude C, or in order for C to be implied. So it's backwards. These are your conjuncts, and then this is your goal, right? All right, so here's another example. So remember, in our knowledge base for the criminal problem, we said for any X that's an American, and for any Y that's a weapon, for any Z that's hostile, if X sells Y to Z, then that implies that X is a criminal, right? So we had the conjuncts, we had the upside down V's, we had the arrow, whatever. Well, here it is written in Prolog, right? So this part right here, the right-hand side in Prolog is actually the left-hand side in first order logic. So these are our conjuncts. American X and weapon Y and sells XYZ and hostile Z. The commas serve as those upside down V's, right? As those conjunction symbols, right? And so if all of these are true, then that implies that X is a criminal. Okay, let's see here. So this right here denotes a list. The first element is E, and L refers to the rest of the list. Because you have to talk about lists, right? I mean, we have the list processing language, and Python is lists, and there's in AI, it's just like there's lists all over the place. Okay, so let's look at a Prolog program for append XYZ, right? So this right here is going to be successful if list Z is a result of appending lists X and Y. So you get Z if you append Y to X, right? If that happens, then this evaluates to true, okay? So here are the statements that you could have in that. So here's the first statement, and there's those periods I was talking about. In Prolog, the end of statements denoted by a period. You know, Java, C++, semicolons, as you know, Python, nothing. I'd say, you know, Lisp, closing curly brace, I guess. Not curly brace, parentheses. So I'd say that, you know, most of the time, probably a good portion of the time, maybe not most of the time, but a huge chunk of the time, you know, when you have some kind of syntax error when you work with Prolog, it's probably because you forgot these stupid periods. They're really easy to forget. You're not used to working with them. They're completely foreign to you, and it's just like, oh my gosh, god darn it, okay, fine. You know, but make sure, first thing you should check if you get some kind of a syntax error is make sure every one of your statements in Prolog's got that period at the end. Okay. So what do each of these sentences mean? Pretty straightforward. You know, I hate reading slides, people, but you know, this language is concise and does it all. So I'm not going to paraphrase it. I'll just go ahead and I'll indulge myself this one time. So what's this saying? Okay, this is saying that if you append an empty list with some list that's we call Y, right? So you have an empty list and you're going to append Y to that empty list, then that's going to produce the exact same list Y. Okay. Now, what this is saying, okay, this second statement saying, is that list AZ is the result of appending list AX onto Y, right? And that's going to be true if Z is a result of appending X onto Y, okay? So, you know, this is just another way of saying, look, you know, you can append two separate lists together, and, you know, as long as they contain both elements, you know, as long as your new list contains elements of both the lists, then you're good, okay? So that's what the result is going to be of that append XYZ. if you've got this append operation. Okay. All right. So a lot of words, sounds really confusing, but here's an example of it executing, right? So if you ran the query append x comma y comma 1 comma 2, okay, what are you asking here, right? You would type this in at the command line of your interpreter, for example, after you've ran your program and loaded up these two rules, okay? Or actually one fact, sorry, and one rule. Okay, so you type in this query, append x, y, 1 comma 2. What are you asking? What two lists can be appended to give 1 comma 2? Right, so you get a list of solutions here, right? This is what the output would be similar to in your interpreter. Okay, it's going through the backwards chaining process, and it's a generator, so you're getting a list of possible solutions. Okay, so what could we get? Well, for x, you could have the empty list, and y could have 1 and 2 in it. So appending y onto x gives you this list right here if x is either empty and y has got 1, 2 in it, or if x has got 1 in it and y has got 2 in it, or x has got 1, 2 in it and y has got nothing in it, right? So these are your three possible solutions. All right. So Prolog executes using, as I mentioned before, it's executing using a depth-first backwards chaining algorithm. And the clauses are going to get tried, they're going to get attempted in the order they appear in the knowledge base. So, it's working top-down, trying to satisfy each of these clauses. So the order in which you actually write stuff in your Prolog knowledge base, your Prolog program, matters, right? Depending on the order in which you write stuff, you might get an answer quicker, or you might not get an answer at all, right? Because things get resolved in a top-down fashion. So sometimes, you might be writing up your logic, doing your planning, writing your stuff up in first-order logic, and then, you type everything into your Prolog program, and then you run your query, and nothing happens, or you get no answer back, right? You fail to unify. Unification fails. So your query returns false, and it doesn't work. So it could just be the case that you got to put your rules and facts in a different order, so that way they can get resolved in the proper order. Okay. All right. So let's talk a little bit more about that problem. With Prolog. I talked about how the order in which I just mentioned how the order in which you list your facts and your rules matters. And we also talked earlier about how the depth first search has problems with search trees. We've got problems if there's repeated states and infinite paths, right? So let's talk about that. Okay, so we want to write a logic program in Prolog to figure out if there's a path between 2 points on a directed graph. Okay, so you could write these two sentences or these two clauses right here, right? So what's this saying? Remember, the right-hand side is the left-hand side in first-order logic. So if this is proved, or if this is true, then this follows, right? So, and then also for this sentence, if both of these are true, then this follows. Okay, so this is saying if there's a link from X to Z, then that implies that there's a path from X to Z. And this is saying right here is that if there's a link from Y to Z and there's a path from X to Y, then you have a path from X to Z. Okay, so if we try to apply these two rules to a graph that has 3 nodes, and that graph is described with these two facts in its knowledge base. There's a link between A and B, and there's a link between B and C. Okay, and so, picture that, right? You can go from A to B, and then you can go from B to Z. Okay, and so these rules are trying to deal with that. Okay, or these rules. Okay, so All right, now take a look at, in figure 9.9, the A graph, right? That's right there. That's the graph that we just talked about with those facts, A to B to C, right? So trying to find a path from A to B to C, depending on the order in which you put your clauses in your knowledge base, your Prolog statements, you could end up having an infinite loop, right? The order in which we list these things could get us into an infinite loop. You're looking at it and you're like, oh, okay, what are you talking about, infinite loop, right? Okay, so here's the proof tree for this graph right here, A to B to C, okay, using knowledge base that contains those two sentences, okay, plus we got link AB and then link BC, right? So we're trying to prove that there's a path from A to C. Now, there's a path from A to C if there's a link from A to C. Now, there's nothing here that's gonna unify, right? We can't resolve link A to C because there is no fact link A to C. There's link A to B and link B to C, right? So we go back, right? So that means that this part right here failed, and so then we go and we try this one, okay? So when we try that guy, we have to prove the two conjuncts, path from A to Y. We'll fill in the A for that first part because that resolves, okay? And then, or we're going to, as we can see when we do the link here. And then we'll have to resolve the right-hand side. So what was the left-hand side? Or excuse me, we'll have to resolve the right conjunct, remember, because these are both conjuncts. So let's go look at the conjuncts. So path XY, link YZ. Path, link, okay? Now, can we resolve link? Is there some fact in our knowledge base where we can plug that in for link BC? Well, yeah, there is, right? But remember, it's depth first search, so it's going to resolve the path first. So path. Now, is there something we can plug in for A, or for both of these terms, right? For both of these arguments. Well, now remember, path, this ends up being a sub-goal. So we go back up here. What do I mean by that? Right here, right? Here's our sub-goal. So in order to deal with this conjunct right here, right, we have to deal with the left-hand side right here if we have to find a substitution for the y. So, right, so for the first part, we can put in, we wanted to prove that there's a path from A to C, so we'll go ahead and plug in for the link, we'll say A and Y, okay? Because we know that there is, in our knowledge base, we know that we've got those two facts, link AB, link BC, right? So now what we want to do is we want to say, okay, well, link A. Is there something we can substitute for Y that'll allow this thing to unify to link AB? Yeah, we can bind B to Y, right? So if we do that, then this becomes link A comma B, right? And so then that gets satisfied, and so then that Y that has B bound to it will then path A comma B, right? That B is also bound to this Y here. So this first conjunct is satisfied, it's proved. So path A comma B. Now you have to do the other conjunct. Well, we already have in our knowledge base the fact link B comma C. So that is proved right there just by grabbing that fact, right? So link B comma C unifies with it straight away. So both of these conjuncts are satisfied, and so then that's the left-hand side for the goal right here, right? And so that proves that it is true that there is a path from A to C, right? But if we got that in the reverse order, right? If we got that in the reverse order, and I'll let you trace through that since I took so long on this first one. If you get it in reverse order, then you end up with a different proof tree is the big idea, right? And you end up basically with infinite recursion. Okay, so I'll leave it as an exercise for you to trace through it to see why. Okay. All right. So the big idea there is that you can end up with an infinite proof tree, right? If the clause is in the wrong order, and that would result in you not being able to get an answer to your query, even though you could if they were in a different order. Okay, so the order matters, and what this means is that Prolog is incomplete as a theorem provider when you have a knowledge base full of definite clauses. Why? Well, for some of the knowledge bases, it can't prove entailed sentences because, and this is the big point, because you can't prove some of the entailed sentences for some of those knowledge bases. Why? Just because we put the order of the sentences wrong. Just because we got the order wrong, so that way the tree ends up generating an infinite, you can end up with an infinite proof tree. So, depending on how the knowledge base is written, you might not get an answer, even though you should. Okay, now forward chaining doesn't have that problem because once path A, comma B, path B, C, path A, C are inferred, your forward chaining is over. Okay, so there are some issues with the backwards chaining algorithm, and different inference engines deal with it in different ways. Prolog lets you blow yourself up, right? And they made a compromise between always making sure that it's complete and efficiency, essentially. I mean, that's the long and the short of it. So it's up to you as the programmer to make sure that your clauses are written in such a way in the knowledge base that you don't end up with an infinite proof tree. Okay, so again, just simply reversing the order of the two sentences causes you to have two different proof trees. One will resolve your query, the other you'll never get an answer for. Okay? All right, so I think we're just about done here. One more thing. Almost forgot. Depth first backwards chaining has problems with the redundant computations. Okay, so that's what this B part over here was, right? So you can have a graph where you're trying to find a path from A1 to J4, right? And we won't go into too much detail about this, but if you've got each node that is connected to two random successor nodes, okay, if that's how the graph is defined, then all of the inferences that have to be made by the backward chaining algorithm, it's going to grow at an exponential rate, essentially, right? So just trying to get from one point to another following these rules causes you to have a ginormous growth in the number of inferences that you need to find that path. So the efficiency can degrade pretty fast. Okay, the amount of inferences can be exponential. Now with forward chaining, you're going to have at most in that scenario n squared, those n squared linking nodes, those n squared successor nodes, right? So n squared is a lot better than exponential. Okay. All right, so let's go ahead and go through the summary of what we talked about in chapter 9. I mean, that's it. That is it. And, if going through the videos, going through the slides, that's still not quite enough, or if maybe my explanation was a little garbled or whatever, you know how to get a hold of me. Shoot me an email, stop by my office hours. I appreciate the opportunity to clarify for you. But at the end of the day, I think I'm trying to save you from having to sift through the textbook, but the textbook is still your overall best bet, right? That's why we still have the reading quizzes and whatnot. So if you're not sure about any particular point, section 9.4, it's like 4 pages long, right? And I didn't cover every single part of those 4 pages. I skipped over some things like, how do you make the backwards chaining algorithm more efficient? Well, the textbook talks about parallelism, right? And you're not going to be responsible for talking about that. If it's not on the slides, then you don't have to worry about it. But it gives you some extra depth, and there's an example of that. And maybe a different, maybe a slightly more clear explanation than what I gave you. Use whatever material you need to get it. Use whichever resource you need to make it clear. And again, you know how to get a hold of me. Email me, stop by my online office hours, whatever you need, I'm at your service. Anyway, so let's summarize. Let's see here. So there's a lot of different algorithms for performing logical inference. One approach uses the inference rules, which are universal instantiation and existential instantiation, which we talked about. That allows you to propositionalize the inference problem. And the main downside to this is that it can be slow. What's unification? You're trying to find a substitution for variables, right? That allows you to eliminate that instantiation step for our proofs from first order. Now, what's the benefit of this? Well, faster. We're increasing the efficiency. By bringing in this concept of unification, we can get around having to do propositionalization, using universal instantiation, existential instantiation. That process slow. Unification can be much faster. All right, so we looked at a lifted version of Modus Ponens called Generalized Modus Ponens, and that can be used, or that utilizes unification to give us that, that inference rule. Forward chaining and backwards chaining, they use this rule. They use generalized Modus Ponens on sets of definite clauses. Forward chaining is often used in deductive databases and production systems. Backwards chaining is used in logic programming systems such as Prologs, right? And one of the main drawbacks to it, the flaws with it, is that you can have these redundant inferences. Remember we talked about in part B of, what was it, graph or figure 9.9, 9.10, trying to get from point A to J10, right? With those two random successor nodes, you can end up doing a heck of a lot more inferences than you need to, slowing things down quite a bit. And with Prolog, just by changing the order of your sentences, you can end up with the infinite recursion, with the infinite loops. And so you never get an answer to your query, right? Which makes the algorithm incomplete, because the order in which you're doing things, the order in which the knowledge base is written, might cause the algorithm to fail to entail sentences or facts that it should be able to entail if it was written in another way, in another order. Okay. All right. So that is everything. All right. I'm gonna just go ahead and build this video. I'm not gonna go back through and edit it. So just to get it up, since I'm late getting it up, from the previous video not storing sound, and I just want to get this up and get it done so that way you have it this week. Again, if there's anything in here that's garbled, that isn't clear, give me a holler and let me know so I can take the opportunity to clarify for you. Okay? Alrighty. Thanks tons, and we'll catch you next time.